Okay, let's dive into something pretty mind-bending today. We usually think of dark matter as this, well, this invisible stuff, right? Just sitting there, pulling things with gravity. But what if it's way more active than that? What if it's actually, alive with its own dynamics, shaping the whole universe? Today, we're doing a deep dive based on a really fascinating paper by J. Elfred. It's called Is the Dark Plasma Universe Shaping the Ordinary Matter Universe? Our mission to explore this groundbreaking idea that maybe a big chunk of dark matter is actually this dynamic, self-interacting plasma,
Hmm.
like a hidden architect for the cosmos. You might come away thinking very differently about, well, pretty much everything. So for ages, dark matter's been the strong, silent type in the universe. We only know it's there because of gravity. But J. Alfred's work, it paints a completely different picture, doesn't it? Way more active. What's the core idea that flips the script?
Well, what's really fascinating here, the core hypothesis, is that a pretty significant chunk of dark matter isn't just particles floating around. It exists in what Alfred calls a self-interacting dark plasma state, especially when it gets close to ordinary matter, like us, like galaxies. And this dark plasma, he suggests it's made of dark matter particles that actually have a weak electric charge. It's governed by something called a hidden U1 gauge symmetry, which sounds complicated, but basically means they can interact with each other through a kind of dark electromagnetism.
A force we can't see. Hidden force.
Exactly. And if you think about it,
Yeah.
look at ordinary matter. Over 99% of what we can see is plasma. Stars, lightning.
Right, yeah.
So the idea that dark matter, especially if it has some kind of charge, could also be plasma, it kind of makes sense, doesn't it?
It does, actually. It feels less weird somehow.
Right. It shifts our view from just passive, collisionless stuff to something dynamic, something that interacts with itself.
Okay, that's a huge shift. But if it's interacting like plasma, it must leave traces, right? Some kind of footprint we could actually look for, even if it is dark. How would we even spot that?
Precisely. If these dark matter particles are bumping into each other, interacting, they should form structures. They should have instabilities. Things like dark shocks, maybe filaments, maybe even dark magnetic fields, similar to what we see in regular plasma clouds in space.
Dark magnetic fields? That's wild.
It is. And the key thing is these aren't just theoretical predictions anymore. These kinds of features,
Hmm.
they've actually been sort of indirectly observed using gravitational lensing.
Ah, lensing, seeing the invisible by how it bends light.
Exactly. We see the effect on light from background galaxies, and that lets us reconstruct where the mass is and sometimes what shape it's taking. And, this isn't just Alfred working in isolation. Back in 2018, the APS Division of Plasma Physics meeting, they concluded dark matter can behave like a cold plasma. It could show plasma instabilities, and these would have observable results.
So the physics community is looking at this seriously.
They are. And interestingly, because that dark charge Alfred talks about is likely weak, these dark plasma effects might be, well, less chaotic than ordinary plasma, maybe clearer structures.
Okay, so theory points to features, and lensing might be seeing hints of them. But the bullet cluster, everyone points to that as proof dark matter is collisionless, right? The dark matter just sailed right through in that collision. How does this dark plasma idea handle that classic example?
That's a really important question. The bullet cluster, yeah, 1E065756, it's the poster child for collisionless dark matter. You see the hot gas, the ordinary matter, smashing together and slowing down in the middle. But the bulk of the mass, detected by lensing the dark matter, seems to have passed right through.
Yeah, like ghosts passing through each other.
Right. And
But-
that's been the standard interpretation. But it might not be the whole story. When you look at other galaxy cluster collisions, things look different. Take clusters like Abel 520 or Abel 3827. In those cases, the dark matter doesn't seem to just sail through. It seems to lag behind or interact more.
Really? How do we know that?
Well, in Abel 3827, for instance, they use gravitational microlensing, tiny distortions of light, and they found dark matter halos actually trailing behind the stars.
Trailing, like they're being dragged.
Exactly.
Yeah.
That implies there's some kind of drag force acting on them, which is what you'd expect if they were moving through a medium, maybe a dark plasma medium that's interacting.
Okay, that's a strong hint of interaction.
It is. And simulations back this up too. If you model cluster mergers and give the dark matter a hidden charge, like Alfred suggests, you can get things like collisionless shocks, not physical bumps, but wave-like interactions plus plasma instabilities, turbulence, all the stuff we see in ordinary astrophysical plasmas.
Like shock waves in space, but made of dark matter.
Sort of, yeah. So the bullet cluster might show one aspect, but these other clusters, they really open the door for a component of dark matter being collisional, like plasma.
Okay, that reinterpretation makes sense. It's not all or nothing. So we've got general behavior, collisions, but what about shaping specific things we see, like those weird faint shells around some elliptical galaxies? How does dark plasma explain those? They look so structured.
Ah, yes, the galactic shells. That's a fascinating piece of the puzzle.
Mm-hmm.
When we use gravitational lensing to map the dark matter around some elliptical galaxies, we don't just see a smooth blob. We see these faint concentric shells,
Mm-hmm.
like ripples. And they extend really far out, sometimes 2 or 3 times further than most of the stars.
Wow.
Yeah, galaxies like NGC 7600, NGC 3923.
Mm-hmm.
They have dozens of these shells. About 10% of ellipticals are even called shell galaxies.
So what was the old explanation for those? Cosmic leftovers.
The traditional idea, yeah, is that they're scars from mergers. A big galaxy eats a smaller one.
Mm-hmm.
And the gravitational interaction creates these ripples, these waves of stars that spread outwards like waves on a pond. It's a plausible gravitational effect,
Okay, makes sense. But Alfred has a different take.
a fundamentally different one. He suggests the shells aren't just stars rearranged by gravity after the fact. He thinks the underlying dark matter halo itself is dark plasma, and that this dark plasma naturally organizes itself into these concentric shells because of its own plasma physics. Its internal dynamics create the pattern.
So the dark matter forms the shells first.
Yes. As Alfred put it back in 2005, the presence of these shells in the dark matter strongly suggests it's in a plasma state. In his view, these dark shells then act as a gravitational template, a mold. The ordinary matter of the stars just fall into that pre-existing pattern.
So the dark matter isn't just a scaffold, it's the sculptor.
Exactly. It's moved from being passive background to the active architect shaping the galaxy from within. That's a huge conceptual leap.
That really is. Okay, so static templates like shells, fine. But what
Okay.
about more dynamic, energetic stuff? Cosmic smash-ups leaving signatures.
All right, the dynamics are key. And there's evidence here, too. Think about those cluster mergers again,
Right.
like Abel 520, the train wreck cluster.
Hmm.
Research back in 2015 by Matti Heikenheimo and his team suggested that a key prediction of this dark plasma model is actually the formation of bow-shaped dark matter shock fronts.
Like the bow wave from a boat.
Pretty much, yeah. And they proposed that these dark shocks might have already been seen in the weak lensing maps of those cluster mergers.
Whoa, already seen.
Potentially.
Mm.
And work by Christian Spithman's group adds weight to this. They noted that in some clusters, the dense core of dark matter seems to coincide with the hot X-ray emitting gas.
Which is unusual if they're totally separate.
Exactly.
Yeah.
It suggests the dark matter component might be behaving dynamically similar to the ordinary plasma. It could be forming shock fronts, dissipating energy, just like the gas does. And their simulations, they showed that this interacting dark plasma component would naturally form structures called Mach cones.
Mach cones, like sonic booms. What does that mean for dark matter?
Yeah. Think sonic boom. When something moves faster than the waves in the medium it's traveling through,
Yeah.
it creates this conical shock wave.
Okay.
In plasma, you get these distinctive vortical cone-shaped structures. If dark plasma can form Mach cones during collisions, it means it's behaving like a fluid, undergoing incredibly energetic dynamic interactions, creating dark sonic booms as it moves.
Cosmic dark sonic booms. That's an image.
It is. And Alfred was using the term dark plasma way back in 2005 to describe exactly this kind of dynamic plasma state behavior for dark matter. So the idea has been building.
Okay, this is painting a picture of dark matter being way more involved than we thought. Galaxies, collisions. What about the biggest scales? The cosmic web.
Right, the largest structure in the universe. The idea of this cosmic web, this vast network of filaments connecting galaxy clusters separated by huge voids, that's been around for decades.
Richard Bond coined the term, right?
That's right, back in '96. The initial hints came from the cosmic microwave background, the CMB. Those tiny temperature fluctuations suggested matter wasn't spread evenly. It suggested dark matter, and the ordinary matter pulled along with it would clump into dense regions and leave vast empty spaces as the universe expanded.
And simulations showed this web-like structure.
Exactly. Cosmologists used supercomputers, fed them data from galaxy surveys, and ran simulations that showed this incredible spongy network emerging, dominated by dark matter filaments. And now, we're not just simulating it. Observations, especially using gravitational lensing on huge scales, have confirmed it. We can actually map parts of this dark cosmic web. It's the universe's skeleton.
So how does Alfred's dark plasma idea fit into this grand cosmic structure?
Well, the proposal is that this cosmic web is essentially made of dark matter in a plasma state. And the ordinary matter, the galaxies we see, are just kind of draped over it, pulled in by gravity.
So the web itself is plasma.
A dark plasma. And that changes things. It means the web isn't static.
Right.
This dark plasma would have pressure, viscosity. It could influence how structures form on all scales. It might suppress the formation of very small dark matter clumps and naturally form these huge filaments and maybe even dark shocks within the web itself.
So it's the blueprint and the dynamics engine.
Pretty much.
Yeah.
It provides the gravitational structure, but also hidden dynamics from the dark sector that shape ordinary matter. And here's a really wild thought. Because of plasma dynamics, these dark filaments in the web could actually be rotating.
Rotating the whole filament.
Yes, and as they rotate, they'd gravitationally tug on the ordinary matter filaments within them, causing the visible parts of the web to rotate too. We might even be seeing hints of that.
That's incredible, like cosmic gears turning.
It is, and it also leads to the idea of dark Birkeland currents. Think of the electrical currents that cause auroras on Earth, but on a cosmic scale, made of dark plasma. Huge, invisible rivers of charged dark matter flowing along the filaments, potentially dragging ordinary plasma along with them.
Mind blown. Okay, this is so much, and it really feels like it changes everything. But to be super clear, let's nail down what this dark plasma isn't, because it sounds like it could get confused easily.
That's really crucial, yes. The terminology needs care. So dark plasma, as Alfred and others like Carol Heikenheim of Spethman describe it, it refers specifically to a plasma made of dark matter particles themselves.
Okay, made of the mystery stuff. So what's the common confusion? What is it definitely not?
It is absolutely not ordinary matter. You know, protons, electrons, it's just hiding in some kind of dark mode.
Plasma in dark mode. I think I've heard that. What's that and why is it different?
Right. Plasma in dark mode would be normal, standard model particles, just really, really cold or diffuse, so they don't emit much light and are hard to see with telescopes.
Like invisible regular gas?
Kind of, yeah. But the problem is gravitational lensing shows these vast dark matter structures that are way, way bigger and more massive than all the visible stuff combined. If those structures were just ordinary matter hiding in dark mode, it would totally contradict everything we know from the CMB and Big Bang nucleosynthesis about how much ordinary matter there can be.
Right, the cosmic budget doesn't allow for that much hidden normal matter.
Exactly. So the idea that these huge dark structures are just ordinary plasma playing hide and seek,
Yeah.
that's pretty much ruled out by the data. It has to be something fundamentally different.
Got it. So let's just recap the key differences. Ordinary plasma, traditional dark matter, and this new dark plasma idea. What sets them apart?
Okay. Ordinary plasma, made of normal charged particles, interacts with light and electromagnetism. We can see it. It feels pressure, which resists collapse. That's stars, nebulae. Traditional dark matter. Invisible, doesn't interact with light, only known through gravity, thought to be cold and collisionless, clumps easily to form structure scaffolds, didn't interact with photons in the early universe, so no CMB imprint.
The standard picture.
Now, dark plasma,
Yeah.
also invisible to our light and electromagnetism, made of dark matter particles, but these particles have their own dark charge and interact via a dark electromagnetic force. So it clumps gravitationally, but also interacts with itself like a plasma forming shocks, filaments may be rotating, governed by its own internal physics, but still invisible to us directly.
Okay. Distinct physics, distinct behavior. That clarifies it.
It's a whole separate interacting sector, just hidden from our view except through gravity.
Right. So putting this all together, what does this dark plasma concept mean for the big picture? Alfred's unified view of the universe.
Well, Alfred proposes a really interesting cosmic invent based on this. He suggests that maybe 70%, the vast majority of all matter, is actually what he calls pseudo or dormant dark plasma.
70%. Okay. What are pseudo and dormant?
Pseudoplasma has charged dark particles, but might be neutral overall, showing plasma traits only near active regions. Dormant dark plasma has charged particles too far apart to interact much, again, unless near dense matter.
So potentially plasma-like, but quiet most of the time.
Exactly. Then he suggests another 15% is active dark plasma, the stuff really doing the dynamic things we've discussed, especially near ordinary matter. And the final 15%, that's active ordinary plasma, the stuff we see.
So only 15% is the visible active universe we know.
In terms of plasma, yes. But notice the active dark plasma and active ordinary plasma together make up 30% of all matter. It's a lot of interacting stuff.
That is a lot. And the overall conclusion then?
The big conclusion Alfred draws is pretty profound. If most dark matter is in some plasma state, active, pseudo, or dormant, and almost all ordinary matter is also plasma, then, broadly speaking, the entire universe, or maybe even a local multiverse if you consider coupled dark sectors, it's fundamentally in a plasma state.
The plasma universe.
Essentially, yes. A universe where dynamic, collective, plasma-like interactions are the norm, governing structure from galaxies to the cosmic web, both seen and unseen.
Wow, what an incredible journey that was. J. Alfred's work really forces a complete rethink, doesn't it? Taking dark matter from just this passive, invisible background to an active, shaping force, a self-interacting dark plasma literally building the
It
universe.
really does. It's a powerful shift in perspective.
Yeah.
The idea that the visible cosmos isn't just adrift in emptiness, but is actually emerging from this intricate, dynamic, invisible plasma template. It fundamentally changes how we might think about reality itself. Plasma dynamics, dark and ordinary, could be the key organizing principle.
It really makes you stop and think. If most of everything, seen and unseen, is this churning, interacting plasma, what other incredibly complex hidden dynamics are playing out right now, shaping everything that we haven't even conceived of yet? Something to definitely ponder next time you look up at the night sky. You're not just seeing stars, you might be looking through layers of invisible dynamic architecture.